Okay, everyone. Can everybody hear me? Would you say yes? Maybe not. So let me check my system. Okay, good. Thank you. Okay, so we will talk about today and possibly a little bit, not next week. Next week is a midterm exam. We don't have any midterm, so you can take a break. But 1 week after, we might talk a little bit more with the topic that we want to discuss is the compactness theorem. So I think in the beginning I said in logic, there are several logicians. Some are from philosophy department, but some are more like mathematicians. But then these mathematicians who work in logic can be grouped into maybe 2 or 3 different groups. One group is called people working on proof theory. The other group is called, usually another big group is it consists of people working on so-called model theory. Okay? And according to what I hear, model theory, the other mathematicians regard model theories very highly because they solved some of the open problems from algebra and so on. Now, according to what I heard from some model theorists, compactness theorem in logic is one of the cornerstones of the model theory. It's one of the most important results in model theory. Sometimes if you study mathematical logic later, you will learn something called soundness and completeness theorems of first-order logic or propositional logic and so on. According to what I heard, the compactness theorem is much more important than these type of some well-known theorem that you encounter in other mathematical logic course. So if you don't understand what I'm saying, the point I'm making is that compactness theorem is very important in mathematical investigation into logic. Also, the compactness theorem is very important for application of the logic in computer science because it enables us to design the automated theorem prover for first-order logic. So it's a very important theorem. And I know that some of you took courses from math department, especially maybe some of you took courses on topology. And then you heard about compactness theorem from topology and compactness property. And this compactness theorem is closely related to the, compactness theorem from topology, especially at a certain level, it can be viewed as equivalent to so-called Tikhonov theorem from topology. So it's a close connection with mathematics. Also, it has a good application in computer science. Okay, so let me give you some motivation about compactness theorem from the computer science perspective. So far, what we studied so far right now is propositional logic, okay? And then after this lecture, so this compactness theorem, we're gonna start to look at predicate logic where we have where we can have a statement like some predicate P is true for some variable X and Y, and then some other predicate Q is true on X, and so on. So far in propositional logic, and maybe also we have some quantification like this. In propositional logic, we don't have this type of quantification. Also, we don't have a predicate symbol. We only have a propositional symbol like a Q. The Q is already here. Maybe propositional symbols like R, but we don't really say this R has this internal structure, which is it's really a predicate P stated on object X and Y. That's not what we're concerned with when we talk about propositional logic. Okay, so that's the kind of logic that we're going to talk about, and this is the logic that people use informally to talk about mathematics and various statements formally. So we're going to look at it, and in particular, we will look at how we can come up with automated theorem proving techniques for predicate logic. But the key idea about what we're going to talk about later is that if we have the following step, which is if we have a predicate logic formula, like the one you see here, later one key step of developing automated theorem proving technique is to convert this predicate logic formula conceptually into infinite set of propositional logic formula. So we're gonna convert this somehow to the infinite set of propositional, maybe using F is better. So we convert this to an infinite set of propositional logic formula like this. And this is from predicate logic. But this one, all of these F are from propositional logic. So which is the logic that we studied so far. Okay, so F1, F2, F3, they will never contain any quantification. They will only be about propositional symbols. Okay, but now if you then we are so suppose I want to design some automated theorem prover for predicate logic formula like the one that we started with, and as I advertised, later we will learn how to convert this predicate logic formula into infinite set of formulas, at least conceptually. But then, because it's an infinite set of formula, I mean, designing any algorithm on this infinite set is going to be very, very difficult, right? If we want to check satisfiability for all the formula together, okay? So then, I mean, it's not quite conceivable to how to, I mean, it's not very easy to think about how to design an algorithm for checking satisfiability. Well, maybe if we want to check unsatisfiability of conjunction of all of these formulas, okay? So then that will also become very difficult to check because you have an infinite set of formula. So what Compactnet theorem allows us to do is to reduce reasoning about this infinite set of formula into finite subsets. So we will do some reasoning about one. So we have an infinite collection of finite subsets like F1, 2, and so on. But they are all finite. And then we'll say some property, the compactness theorem says some property related to satisfiability or unsatisfiability for all these formulas in the infinite set can be reduced to satisfiability or unsatisfiability for finite subsets of this infinite set. Okay. Now, if you have a finite subset, then we can do some reasoning about this guy, this guy. I mean, this finite set really represents the conjunction. So we can invoke DPLL or some variable elimination algorithm to check F1 is satisfiable or not, F1 and F2 is satisfiable or not. This we will see that Compactness theorem allows us to use these algorithms that we learned before to answer some of the questions about this family of these finite sets that can be translated into some properties about this infinite set. So just to sum up, we will later talk about predicate formula, which is a much more expressive logic than what we studied so far. But then the key step there is to reduce the predicate formula into infinite set of propositional logic formula. And then the compactness theorem will allow us to reason about, in other words, to answer some satisfiability or unsatisfiability questions about this infinite set of formula by reducing this reasoning about infinite set into finite subsets. Okay. Right. Then let's look at the next. So to talk about, so the key player that we're gonna, we will key object that we will manipulate is a bit different from what we studied so far. So the key object that we will manipulate is an infinite set of formulas. So the key object we're gonna deal with is an infinite set of propositional logic formula. So far, when we talk about algorithms, we only think about specific one particular formula or finite, collection of the propositional logic formula. We hardly talk about infinite set of propositional logic formula, but this is the main player today. And then because there are infinite set of propositional logic formula, if we collect propositional variable appearing in F1, F2, and so on, that's gonna typically form an infinite set. If we enumerate, that's going to be P1, P2, and so on. So these are the propositional variable that appears in this infinite set of formula. So this is going to be a typical situation. Okay, so we are dealing with some infinite stops in this lecture. Now, in this context, the notion of the partial assignment becomes very important. And then also the notion of extension between partial assignment will be very important. Partial assignment is nothing but a mapping from subsets of propositional variable to 0 and 1. Okay, so full assignment, but non-partial assignment is a mapping that assigns 0 and 1 to all the variable here. So maybe assign 0 to P1, 1 to P2, and so on. For everything, that's going to be full assignments. Full was just usual assignment. But partial assignment will only be we maps values to finite subset. I mean, typically finite subset, but it doesn't have to be a finite subset. So one example of partial assignment will be it maps P1 to 0. Maybe it will skip P2, but it may map P3 to 1. So this is one example of partial assignment. And then among the partial assignment, we will define the notion of extension. And this is intuitively, it really means extending. Okay, so if you have two partial assignments, one is A, that's written here, another is A prime, and then P3, 1, P4, P0. And we say A prime, it extends A because domain of A prime includes domain of A. So it defines, it does provide a binding for P1 and P3, which are bound in A. And also for the binding that exists in A and A prime say exactly the same thing. So, and then it just add one extra binding, which is P4 gets bound to 0. So if that happens, then we say A prime is an extension of A. Okay, so this is a extension case, but non-example of the extension is a double prime, where if it maps P1 to 1 and P3 to 1 and P4 to 0, then this is not a good example of extension of A, because this, see, I mean, where it binds 1 to P1. On the other hand, in A, 0, I mean, P1 is bound to 0. Okay? And so extension has to satisfy domain should be larger. And then for all the existing variables, values should get exactly the same. I mean, the binding should be exactly the same. So domain should be larger. And for all the existing variable in the small assignment, this A and large assignment should say exactly the same thing. This will play a very important role in our proof of compactness theorem. Okay. So just to recap, what we have is the main player of this lecture is an infinite set of propositional logic formula. Our assignment is typically the mapping from this infinite set of propositional variable to values. And then we are concerned with partial assignment, which map only some propositional variable to 0 and 1, and we define the notion of extension between partial assignments. Now now we can start to ask satisfiability of a set of formulas. So here a set can be finite, but it can also be infinite. Okay, so maybe showing this better. So we have a set of formula S. So it's going to be a set of propositional logic formula. It can be finite, something like this, but the typical situation that we are concerned with is going to be infinite set. F3, F4, and goes on forever. Okay? And then we say that this set of formula is satisfiable if we can find an assignment, maybe assignment A, such that every formula in that set is true under this assignment. Okay? Intuitively, what this means is this assignment A in this above examples is going to satisfy all the formulas in this set. Okay, so Fi is in S. I mean, this is not a propositional logic formula. That's because this set S can be infinite. So we are taking the infinitary conjunction. So it's not really a propositional logic formula. So I'm just writing it to tell you what this satisfiability, how this satisfiability deal with this all the element in A. It just consider this set S as a intuitively conjunction, infinitary conjunctions of all the formula that appears in S. Also, another point that I want to make is this each fi doesn't have to be a clause, okay? It doesn't, it's not necessarily a clause. It can be an arbitrary propositional logic formula. I mean, if it's a clause, that's good, but it doesn't have to be. This compactness theorem we're going to talk about equally applies to any cases. Okay. So here's an exercise I want you to solve. I will give you maybe 1 minute. So try to find a satisfying assignment A for the set of formulas that you see on the bottom. This is an infinite set of formula, and no. So in propositional logic, we don't allow infinitary conjunction and disjunction. And there are some extension of propositional logic where you can do infinitary conjunction and disjunction. Right now, no. I'm using this notation just to give you some idea of what's really happening. So it's just my own notation here, but in propositional logic, we are not allowing infinitary conjunction and disjunction. So I'll give you 2 minutes to try to construct the satisfying assignment for this infinite set of formula. So, okay, so there can be multiple answers for this question, but here's a one answer. So our answer is that for each of pi, if pi is odd, we assign pi to 1. If pi is even, then we're going to assign this pi to 0. So A here is going to be an infinite assignment. Okay, so A, if I just draw my enumeration form, yeah, maybe using this is better. It will map P1 to 1, P2 to 0, P3 to 1, P4 to 0, and so on. Okay, so then this will satisfy every formula appearing in A. That's because for all the odd formulas, like the first guy, the third guy, they're gonna be true because of odd propositional variable like P1 and P3 that will receive value 1. For the even propositional logic formula here, that will also be true under A because it's even propositional variable will receive a value 0 here. Okay, so that it satisfies every formula. So note that single assignment here, when we talk about satisfiability of entire S, we are looking for a single assignment that make every formula true. Okay, we are not allowing you to choose different assignment for different formula. Okay, for every formula, we want only one assignment to make every formula true. Okay. Okay, so let's now see the statement of compactness theorem. So here's the statement of the compactness theorem. So the compactness theorem say typically this theorem makes sense when S is an infinite set of propositional logic formula. In this context, we're gonna consider countable set of propositional logic, countably infinite set of propositional logic formula. So that's going to be S, our S here. So S mean the, oh, where is, okay. S we in, so when you read this theorem, imagine that we have S, which is a countably infinite set of propositional logic formula. Okay. So then this theorem said this S is a satisfiable, which means there is a single assignment that make this set of propositional logic formula true if and only if every finite subset of S is satisfiable, which means that whatever finite subset you pick, so the finite, so this guy say one finite subset can be F2 and F3. This becomes satisfiable. Maybe if I pick different subset like F2, F3, and F4, this is also satisfiable and so on. So this talk about every finite subset is satisfiable. And this one say entire S is satisfiable. And then compactness theorem say they are equivalent. I mean, these two things say the same thing. One way to understand like many mathematical statements is actually feel the actual contents of the theorem. Okay, why this theorem say something non-obvious. So here's one exercise I want you to do. Maybe I show you two exercises together. So here are two exercises I want you to do. First, one direction of this compactness theorem is obvious, and the other direction is not obvious. Okay, that direction is it requires non-trivial reasoning. Okay, try to identify which direction is an obvious direction, which direction is not an obvious direction, and try to think about why this non-obvious direction is actually non-obvious. I mean, actually feeling some contents of a theorem is the first step of appreciating the theorem. So that's an exercise one. Exercise two is that if you take this theorem and do a little bit of manipulations, that can help you to come up with a semi-algorithm for checking the unsatisfiability, not a satisfiability, unsatisfiability of a countably infinite set of formulas. So S is like this. Assume that we have an iterator for every element in this countable set of infinite formula. Okay, so I mean, it's like a Java object. If you call it, you first return F1, call it again, you return F2, and so on. So you have an iterator for this infinite set of formulas. And then if we use this compactness theorem, you can design an algorithm, semi-algorithm, that can check unsatisfiability for this infinite set of propositional logic formula. And I said semi-algorithm. I think maybe. So here, instead of algorithm, which means that if this algorithm, if S is unset, then this our algorithm should return unset. It should terminate and should return unset. But if S is satisfiable, the other case, then algorithm may return that it can take two possibilities. It may return set, or it goes up into infinite loop. So because of this infinite loop possibility, this is called semi-algorithm. If this possibility doesn't exist, then this is called algorithm because it always terminates, give the right answer. If it goes into the infinite loop when the answer is no, then this is called semi-algorithm, and it's related to so-called recursively enumerable set from computability theory. But anyhow, if you use this compactness theorem and then what you learned so far, you can design this semi-algorithm. And so try to solve both of these problems. I will give you maybe 3 minutes to think about both. So, okay, let me show you the answer here. The for first exercise, the obvious direction is this only direction. And that is because, maybe use a different color. So the obvious direction is this only direction. That is because the, I mean, yeah, we're like, if you look at the semantic, what the satisfiability really means, you can immediately get the answer. So if an infinite set of formula S is satisfiable, then that will be an assignment A under which for every formula in S will be true. So if A is this is true, there's a single assignment A that will make all the formula true for all formula in S. Okay. So then now we can use this assignment to meet this satisfiability claim about satisfiability for finite subset. So any finite subset you pick, for instance, this is a finite subset, is to show, I mean, this direction, we should be able to construct satisfying assignment for this finite subset. And that is quite easy. We can just reuse A. A is really good. It satisfies everything. So it's gonna also satisfy F1, F2, and F3. So the same A will satisfy A, F2, and also A will satisfy F3. Satisfy F3, and you also satisfy F4. Okay, so the mean, this direction of on-if direction is easy. On the other hand, going to the other direction, this if direction is difficult. But why is that? I mean, if you think about what this if direction really tells us, it says something quite interesting. It says that for every finite subset of S, we know it's a satisfiable. For instance, we know that we use a color here. We know that this one is a satisfiable, so it will be satisfiable under assignment A1. Also, another finite subset, this one is satisfiable under assignment A2 and so on. So for each finite subset, we have a satisfying assignment. But now, what's claimed on the left-hand side of this if and only if, which is this part of the if and only if, it claims that there is a single A that make every F true. Okay, instead of A1 for this subset, A2 for this subset, we should have a 1A that make every F to be true. So we somehow, this theorem somehow tells us from this A1, A2, and so on, there is some, if we have this kind of A1, A2, and so on, there is some way, I mean, although it requires a bit more thinking, there is some way to convert this A1 and A2 into a single satisfying assignment A for all the formulas appearing in S. Okay? So that part is a non-obvious part. But it's kind of telling us we can somehow mix these partial solutions like A1 and A2 together to construct really the solution for the entire thing. So that's what this compactness theorem tells us. And that's the non-obvious direction. So this is the non-obvious. Okay, now how to use this compactness theorem to solve the second problem, which is, in this case, we are more interested in unsatisfiability. We want to show unsatisfiability means contradiction. We want to derive a contradiction from infinite set of formulas, okay, propositional logic formula. So now how can we do it? Now, to derive an algorithm for this exercise 2, we take so-called contrapositive of this statement. I mean, contrapositive in Korean means 대우. So if you take a contrapositive, so let me just erase a little bit, make some space. So if I take contrapositive, then contrapositive amount to negating left-hand side of the if and only if, right-hand side of the if and only if. I mean, it's not actually contrapositive. We are just taking negation for both sides of if and only if. Then if a set of formula is not satisfiable, which means that whatever assignment we pick, there is some formula in S which is not true. Okay, so we will never be able to find a single assignment A that make every formula true. So there is always something that escapes. So the entire set of formula is not satisfiable. So if and only if, because each finite subset is for all. So if you take its negation, that means there exists some finite subset of S is unset. So what does this mean? If you take a negation for both sides, it said infinite set of formula is unsatisfiable precisely when, if and only if, some finite subset of S is unsatisfiable. Okay, so if this is the case, there exists some finite subset of S that becomes unsatisfiable. So then what's the strategy for designing an algorithm? We try to search for such a finite subset. Okay, so if we have an enumerator for S, like you have an iterator which returns a single call, it returns F1, we call it again, it returns F2, call it again, it returns F3, and so on. So then we have a while, we put on while loops that gets a new element from S by calling this iterator. Okay, so then initially we have just F1, and then we check F1 is unsatisfiable or not. If F1 is unsatisfiable, so then that means, I mean, if F1 is, there's no way to make F1 true, then this entire S will be it's maybe impossible to make it true either. So if F1 is unset, we say unset. Now, if F1 is satisfiable, that can be done by DPLL, was the variable elimination. We call the next guy that will return F1 and F2. So now we get F2, and we take their conjunctions and check whether it's satisfiable or not. If it's unset, then we return unset. Otherwise, we continue and generate next guy, F1, F2, and F3. And then you do the same thing. Okay. Now, this Compactness Theorem, what it guarantees is that it guarantees if the formula S is unsatisfiable, then this process will terminate at some point because there is a finite subset which is not satisfiable. So this process will terminate at some point and return on unsatisfiability. If S is satisfiable, this process will go on forever. So we will hit this infinite loop, but that is okay because we are only asking for semi-algorithm. So here's a more detailed descriptions about the algorithm. So the design of this algorithm, this semi-algorithm, is using the contrapositive of a non-trivial direction of compactness theorem. So I said non-trivial direction is if direction. If you take a contrapositive, that means a set of formula S is unset, then some finite subset of S is unset. So that's the contrapositive of non-trivial direction. So that's what's written on the next slide. So if a set of formula is unsatisfiable, then some finite subset is unsatisfiable. So this is a property we are using. And then the procedure, so semi-algorithm that it uses, it enumerates S by some algorithm by calling iterator. So you look at the first guy and the first and second guy, first, second, and third guy, and so on. So you have a while loop that look at for the first n prefix for every n. So that's what step 2. And then it called either DPLL or this variable elimination to check this conjunction of F1 up to Fn, while this finite subset is unsatisfiable. If this finite subset is unsatisfiable, it returns that, okay, it's unsatisfiable. Otherwise, it continues. Then compactness theorem guarantees, what it guarantees is if S is unset, this entire process will terminate and then produce the right answer. That's what's guaranteed by the compactness theorem. Okay. Right. So now what we're gonna do is we will prove this compactness theorem. So the non-obvious direction, we're gonna prove this, which means the non-obvious direction is if every finite subset of S is satisfiable, then all S is satisfiable. So that's the non-trivial direction. So this is the non-trivial direction. That's what we're gonna prove. And then the proof consists of the following steps. It has some structure. Then let me show you some overall kind of big picture about the proof. So if we give you the statement of the theorem here. Okay, so this is what we want to prove. So we want to show if direction of this statement. So what we do is we first assume we are given S, which is an infinite set of countably infinite set of propositional logic formula. We assume that every finite subset of S is satisfiable. So we are showing if directions. We are assuming this condition of if. And then we have to construct the satisfying assignment for all formulas in S. So we do it but to do so, there's one very important concept we have to talk about. We say that a partial assignment A, so A is not a total assignment. It may miss some propositional variable. We say the partial assignment of A is good if every formula F appearing in S if f only uses variables that appears in the domain of A, then that formula should be true under A. So I think my explanation may be a bit confusing, but it's quite easy. So if, for instance, A, I think the example is that if A is a mapping which map P1 to 1, maybe P2 to 0, and maybe P3 to 1, then this assignment is good if for whenever we have a formula F in S, if all the propositional variable used in F is P1 or P2 or P3, but it's not using like a P4 or P5. It's only using P1, P2, P3. If that's the case, then A will satisfy F. If this is true, so then we said this A is a good partial assignment. So what it really in some sense tells us is, I mean, A only defines values for propositional variable P1, P2, P3. So as far as what it's for the variables it's defined by A, it doesn't make any mistake, okay? Because any formula that you pick from S, if F is only about P1, P2, P3, the formula A will satisfy F. Okay? So it's a kind of partial solution for the entire problem. Entire problem is you want to come up with assignment that will make every formula in S to be true, and A is a kind of good partial solution. So it doesn't cause any problem for as long as we only concern with the formulas appropriate for A. Okay, so then with the proof, so this good notion of good is extremely important. I mean, this is the key concept that appears in the proof. So then I should show you. Yeah, so here's how the rest of the proof works. We're gonna construct, I mean, not in the algorithmic sense, but in some mathematical sense, we're gonna construct partial assignment A0, A1, A2, and so on, but they will be all good, okay? So they are gonna be all good partial, A0 is a good partial assignment, A1 is a good partial assignment, A2 will also be a good partial assignment, okay? And then it will satisfy two additional conditions. The condition number one is AN, if we pick AN and look at its domain is going to be P1, P2 up to Pn. What does that mean? That means that I said the good partial assignment is a bit like a partial solutions. So in some sense, the AN is an improvement of AN minus 1 in the sense that it's a better partial solutions than before. So the technical condition is domain of AN will be a set of P1 up to Pn. So that's a condition number one. Condition number two is this sequence is compatible. So if for each of AN plus 1 extends AN. Okay, so one example sequence of this. So this extension requirement to say one possibility of this AN, A0, A1, A2 will maybe look like this. A0 doesn't do anything because it's an empty map. A1 may map P1 to 0, but because the domain of A1 should be P1, so it should map P1 to something, but it may be mapped to P1 to 0. For A2, it may map P1 to 0 and P2 to 1. And then A3 will map P1 to 0, P2 to 1, and P3 to 0, and so on. But one important fact here is you look at P1, the next guy is an extension of this. So the value of P1 is fixed. It's going to be the same for all those A2, A3, and so on. So the value of P1 is same everywhere except the first, this first empty assignment. And then also if you look at the value for P2, it's going to be bound to 1, but everything that follows should be an extension of this A2. this value, the binding for P2 should be fixed. So it should be mapped to 1 for everywhere, and so on. So you can kind of view that this, if we managed, during the proof, we constructed such a sequence A0, A1, and A2. So that's the constructing this sequence is a core part of the proof. You can see that this is gradually we are improved. We are getting A0 is a partial solutions, but by moving from A0, A1, our partial solution is better because it deal with more variables. And then moving from A1 and A2, our solution becomes even better, and so on. Sorry. Yeah. So A1 and A2 and so on. Okay. Yeah, sorry about this. So somebody just knocked my door. Okay, so that's the sequence of A0, A1, and A2. Now, if we have such a sequence, this sequence will be infinite typically because there are infinitely many, countably infinite number of the propositional variable. Okay. Now, if we have this consistent infinite sequence of partial solutions or good partial assignments, but the extending good partial assignments, then we can put them together. So this is step number 2, is a process of putting these all of ANs together and construct a one big assignment. In this case, it's going to be a total assignment. And the way we do it is we construct A, but to assign the value of a Pn, we look at nth partial assignment in the sequence and look up its value Pn. And then one thing that you notice, because Am plus 1, Am plus 2, and so on, they are all going to be an extension of An. This will be same as Am plus 1 Pn, Am plus 2 Pn, and so on. Okay. So yeah, so that's how we're gonna do the proof. So something I want you to try is say that in this, I will claim this A it actually satisfies the entire this set of formula S. Okay, so try to show why that's the case. So don't worry about how we build the sequence in step 1, but assume that we can do it. Okay, and under that assumption, we can do step 2. Step 2 is just a definition of A. Now, if we define A according to step 2, we can actually prove A satisfies every formula in the original set S. So show this. I will give you 2 minutes to think about this. Okay, so let me show you the answer for here. I mean, actually, I have a proof. So here's an answer for this. Okay, we want to show that this A constructed in step 2 satisfy all the formulas in F. So we pick any formula F in S, and then look at which variable that formula is using. That formula is using, say, P1 up to Pn. So then, because AN is a good set, so it may be using a bit, it may not, like it may be missing the P2, but it doesn't matter. We just look at all the formulas up to P1 and Pn that includes all the variables P1 up to Pn that includes all the propositional variables that appears in F. Okay, so this P1 up to Pn includes all the propositional variables appearing in F. And it's always possible because formula is finite. So then if we know that this AN is a good assignment, good partial assignment, also the domain of AN is P1 up to Pn. Okay, so that means this goodness of AN, and also another property, the domain of AN is exactly P1 up to Pn, implies AN should satisfy F. Okay, so that's our definition of something good. So this property should be true because AN is good. And then the domain of AN is equal to P1 up to Pn. And good means as far as some formula is using propositional variable in the domain, AN will satisfy this. So by this definition of good, this is going to be true. Now, if you look at A, okay, A is actually the same as AN. I mean, A is an extension of AN. So for all propositional variable Pi, maybe just writing this way is a bit easier to see. So one thing we do know is that if we define A according to step 2, then one thing we know is A of P1 will be the same as AN of P1. That's because A of P1 is same as A1 of P1, but A1 of P1 is same as A2 of P1 and so on. So A of P1 is same as AN of P1. A of P2 will be same as AN of P2. So if we keep going on, so that A of Pn will be same as AN of Pn. Okay. So for all the propositional variable P1 of the Pn, AN and A will say exactly the same thing. And because of this, if AN satisfies the formula F, then A will also satisfy that formula. Okay. So that's how we did this. Step 2 tells us, okay, A is the solution that we are looking for. Okay. So where we are, so we are here. We try to prove the non-trivial direction of compactness theorem, which is if directions. And the big picture of the proof strategy is that our proof will consist of 2 steps. The step number 1, yes. So we are assuming the set of propositional variable is countably infinite. Yes. Okay. So that for step number 1, we construct this sequence of good partial assignment A0, A1, A2, and so on. That satisfies some property. Step 2, we put these good partial assignment together. That's possible because of specific construction that we are doing in step 1. Once you do it, we are done. This is A constructed from the step 2 is going to be the satisfying assignment for all the formulas. Okay. Then if you take a step back and think about, I didn't really mention where we didn't use these assumptions, okay, yet. Okay, so the assumption here is this each finite subset of S is satisfiable. So that's an assumption we have to use somewhere, and that's gonna be used in this step 1. Okay. Without this, we will not be able to construct this infinite sequence of good partial assignment with certain properties. Okay, so let's now go to this step 1 and see how we can prove this. So let me put this slide into these positions. So this step one is what we're gonna prove. So once you do it, then we complete the proof of compactness theorem. Now the question becomes how to do this proof. And the proof here is a bit like, I mean, it's not exactly the algorithm, but it's a bit like some algorithmic flavor because it's an inductive construction. And then to construct this is good sequence of good partial assignment with certain property, we have to ensure one more condition. It's a bit like doing inductive proof. So we will ensure one more property, which is that, so we'll build, maybe just show the next slide. Right. So we will build A0, and then from first build A0, and then we'll build A1 and A2 and so on. So we'll build this sequence one by one, starting from the beginning. And of course, that's whenever we build a sequence, it has to satisfy basic requirement, which is it should be a good. Also, it should extend. Also, the domain should be like this. These are the three requirements we should satisfy, but we will try to satisfy one more, and that will enable us to this inductive construction. This condition is for each AN, there are infinitely many good extensions. So there are infinitely many good extensions of AN whose domains are P1 up to PM. Okay, so AN, whenever we construct this sequence, we will always ensure that AN will have a, I mean, in my mind, if all these extensions lives up above AN, so we'll have some AN prime, maybe AN double prime, AN triple prime. They are all different. There are infinitely many of these guys. And then if you look at the domain of this extension AN triple prime of AN, its domain will be P1, P2, up to some PM triple prime. And then maybe the domain of, it's not actually equality. Okay, triple prime, its domain is like this. And if you look at the domain of AN prime, then maybe again P1, P2, up to some PM prime. So you will have this property. Because there are infinitely many, that means, so what are the consequences? The consequences that because there are infinitely many such guys, if you say set n is set 3, then if you pick any number like, so m to be 20, so then there will be, no. So if you pick any superset of this domain, so like P1 up to P20, which will definitely include P1, P2, and P3. Okay, if you have something like this, so then if I have a P1 up to P20, then there will be some A prime extension. So extension of AN, some extension exists such that its domain will include this guy. Okay. We have a AN, and then there are infinitely many extensions, all of which are defined over some kind of prefix that P1 up to PK. So if we pick any the propositional variable P1 up to some point like a P20, there will be some extension of AN, whose domain includes this guy. Okay, so that's the consequence of this statement. Okay, just to say it again, we want extra invariant we want to guarantee is for every AN, there are infinitely many good extensions. So it has to be also good extensions of AN, whose domains are consecutive segments of PIs from the beginning. Okay, so that's what this property is telling us. Okay, So we will do inductive construction that will satisfy these four properties. Okay. So now to do inductive construction, we have to first deal with the base case. The base case is when A0 is an empty set. Okay. Now we have to show that this empty set, yes, it satisfies this domain requirement. This domain is an empty set, so it satisfies this requirement. There is nothing to worry about this extension because there's nothing, no previous partial assignment, so the extension requirement is also okay. Good. This is it's a good partial assignment because if my propositional logic formula, so no, my set of this S, okay, this S contains what we have. So if it contains some propositional logic formula that doesn't use any propositional variable at all, so that to check the goodness, we have to think about any propositional logic formula in S which doesn't use any propositional variable at all. So then that has to be satisfiable because otherwise, this doesn't satisfy these assumptions that we have. Assumption is any finite subset of S is satisfiable. Okay. So these three requirements are true, and the only extra things we have to make sure is the fourth requirements. So I'll give you 1 minute, 2 minutes to think about this from assumptions that we have, which is any finite subset of S is satisfiable. We can actually show, this invariant part is okay for this base case. Okay, so think about this in 2 minutes. Okay, so let me tell you why this is true. What we have to prove is, this empty partial assignment satisfy this invariant property. And so what we do is that we consider set of propositional variable P1 up to Pm for every M. For M. So then now we collect all the formulas in S that uses only these variables. So now we collect, say, Sm. That's going to be all the formulas in S such that F uses variables in, let's call this one as a variable Pm in Vm only. And this set Sm may be infinite, okay? It doesn't have to be finite. But if you look at, they equate two formulas which are logically equivalent. So then this Sn will become finite, but then there exists some finitely many formulas such that maybe prime this, and let's just erase. So finite many formulas in Sm that covers all the other formulas. So whenever all other formula in Sm, f is logically equivalent to f prime of I for some I. Why that's the case? That's, I mean, the reason is that because if there are only finitely many variables P1 up to Pm, there are only finitely many propositional logic formula that you can write, non-equivalent propositional logic formula that you can write. I mean, actually the number is, there are only these 2 to the, I think 2 to the m. I mean, these many finite formulas are there. So you can pick always finitely many formula such that any other things are actually equivalent to the fi prime. Now for these guys, because it's a finite subset of S, then there is a satisfying assignment for this finite subset. So there's a satisfying assignment, say A prime of say N, which is satisfies all of these guys. So it satisfies F1 prime and Fn prime. So, and then because every formula in Sm is equivalent to some Fi prime, so we can also see that A and prime will satisfy entire Sm. Okay. So I mean, just a bit informal notation, but this means every formula in Sm will be true under A and prime. So what this shows is that A and prime is a good partial assignment. And such that, I mean, when we choose AM prime here, we can be sure AM prime is set values for all the variable in P1 and PM and only those variables. I mean, this is a good partial assignment with the domain of AM prime is equal to P1 up to PM. Okay. So what we did, we start with the collection of propositional variable P1 up to PM. And then by using our assumptions, which is assumption is used here, by using our assumptions, we are able to construct good partial assignments whose domain is exactly from P1 up to PM, and then that is good. I mean, any formula in S using only these variables will be true under AM prime. So that's exactly this condition here. I mean, that's the part of the condition, but our A0 is an empty, so anything can extend A0. So we are done. So we found this guy, and that AN prime will be an extension of A0. Okay, so it has to be an extension. That part is true because A0 is nothing, and then this is good by construction. And because we can do this for every M, there are infinitely many good extensions here. Okay. Now we have remaining 5 minutes. We can actually complete the proof here. So right. So now there's an inductive step. Then for the inductive step, I think a good way to understand an inductive step is really imagining essentially it's a bit like a so-called pigeonhole principle. In Korean, it's called 비둘기집 원리. So this is like a pigeonhole principle. So we are in the middle of constructing this sequence. We are constructed sequence up to AN. Okay, so let's show you the property we care about. Okay, so we construct the sequence so that the sequence satisfies all these conditions, also it satisfies this invariant. So then we want to extend AN by So our goal here is to add an plus 1. So how you do it? So that's the question here. Okay, so I will show you the proof and maybe leave you to show this an plus 1, why an plus 1 is good as an exercise that you can do at home. I think you have to really go through the proof again in your home to really digest what's really happening. So now we have to add one more thing, which is an plus 1. Now the question is how you can do it. So the one way you can do this is we consider the two extensions of an. So an put a binding of all the propositional variable up to Pn. Okay, so an plus 1, we should provide one more binding for Pn plus 1. So that we consider both possible extensions. So B0 is an extension of an where Pn plus 1 is bound to 0. Okay, and B1 is an extension of an where Pn plus 1 is bound to 1. So these are the only two possibilities. Now, if you do this, then we now look at the extension of an. So because of the invariant property here, because of this invariant property here, there are infinitely many good extensions with a certain property on each domain. So there are one extension of this guy, another extension of an, third extension of a, and so on. So there are infinitely many good extensions. Now, if we set B0 and B1 in this way, and then only focus on what's called a proper extension, which means it's not same as an. So we assume that all these guys are different from an. So then an plus, these extensions is either have to go through B0 or have to go through B1 because and this extension of an should provide extra binding for propositional variable Pm plus 1, Pm plus 2 up to Pm. So if we do case analysis for Pn plus 1 and say it's either binding 0 or 1, then maybe all of these guys should be considered as an extensions of either P0. It's an extension of this guy. Maybe this guy is an extension of B1. Maybe this is an extension of B0 and so on. So everything is either extension of either B0 or B1. Okay? There are infinitely many extensions, and then they all belong to either B0 or extension of B0 or extension of B1. So that means either extensions of B0, there are infinitely many extensions of B0 or infinitely many extensions of B1. So the reasoning, there are infinitely many guys, and then you, in a sense, split them into something that extends B0, something that extends B1. Then at least one of the, this set may be finite, but then if that's the case, this has to be infinite. Because, if it's finite, union of two finite set is finite, so one of them has to be infinite at least, okay? So we pick this PBI, either P0, P1 that have infinitely many good extensions and set an plus 1 to this guy. So if B0 has an infinitely many extension, an plus 1 will be B0. Okay. So then we can prove this Bn plus 1 actually satisfies all the conditions that we talked about. It's a good partial assignment. Its domain is from P1 up to Pn plus Pn plus 1. And then also it's an extension of an. And also this inductive property, invariant properties are also going to be true because of this case analysis that we have done here. Okay. So I'm not showing the proof of proving this an plus 1 is good, but I strongly encourage you to do this. This can be proved. It's not very difficult, and you can prove this. Okay. So, the time's up. Let me spend maybe one more minute. So I just show you this slide, and then the proof I done is inductive, but it's not constructive in the sense that it doesn't provide any algorithms. But this kind of proof appears quite often in mathematics. And then I kind of, well, maybe it's better to stop here. So let me just go back to the theorem and then state it one more time, and then just stop there. So here's the compactness theorem we proved. The compactness theorem said a set of countably infinite set of formula is satisfiable if and only if every finite subset is satisfiable. We said only if direction, so going from infinite satisfiability to finite satisfiability is easy, but the other direction is hard. To show this, the other direction, we constructed the infinite sequence of partial solutions, or partial good assignments. And then by putting them together, we were able to construct assignment that satisfy all the formula in S. Okay, so that's it for today, and I will remain here for about 5 minutes. And if you have any question, you can ask me. Okay, so have a nice break next week, and then see you all in 1 week later.